This is a walkthrough project for the binomial distribution, chapter 5 kind of project. And we're going to look at two things. We're going to look at left versus right hand, and then we're going to look at the binomial distribution with a question you guys were asked in the survey of whether you'll be attacked by a bear, mauled by a bear, or attacked by a swarm of bees. Just a couple kind of fun little activities here. So for the first one, we're going to look at left versus right-handed. 10% of the world is left-handed. 1% of the population is ambidextrous. We want to set up a probability distribution based on the theoretical percentages and figure out the expected number of non-right-handers we are going to have in our sample. And so, the first thing we gotta do is look at how many we have in our sample. So let's pull up, and this again, this may be different number based on what semester you're in. So I gotta find my left hand, right hand. There's the attack by bears. We need that. And there you go. So I'll just copy this down. Control C. Control V. And then what I'm going to do is I'm going to sort it. So by column 1. Okay. So we just got to make sure we don't have any issues. So both left then right. And we'll just come down and make sure there's nothing at the end. Okay, so 59 people. We have enough sample here. And so we're going to look at this percentages. We have 89% is right, 10% is left, 1% is ambidextrous. And then if we multiply these by our sample size, we can get our expected amount. So 59 times 0.98 is going to be 52.51. And 59 times 0.10 or 10% is going to be 5.9. And then 0.1 time, or 0.01 times 59 is going to be 0.59. And we can add these up. So points plus 0.5.9 plus 0.59 gives us back our 59. So that should always add up to the same amount. And this has to add up to 1. Alright, so what expected number of students on a sample size should not be right-handed dominant? Well, we're looking at the 5.9 and 0.59. And we see about 6.49 is not going to be right-handed dominant. Alright, so now we want to base this on the binomial distribution. And so binomial distribution has a few important traits. One is fixed number of trials. We have n equals 59, so we have that. Okay. Next one is each trial is independent. Well, we have that. Each student's going to be independent. I don't know why there's trials. Okay, need an S there. Next one is we have a probability of success and a probability of failure. I spelled probability wrong. Oh, there you go. Forgot the B. Right, and then the last one is that our probability of success is constant. Probability of success is constant. Okay. Now, in success, in our case, is going to be not right-handed, basically. So our probability of success is basically 11% here. So P of S, or actually I'm just going to call it P, is equal to 0.11. And the two success and failure, that's going to be right, left-handed. What determines that? Alright, so we do have the conditions for binomial distribution. We have fixed number of trials of 59. Each trial is independent. We have a probability of success and probability of failure. Basically, we have two options, either right-handed or left-handed, and the probability of success is only 0.11. Success again being not right-hand dominant for this. I think I keep that. Yeah, non-right-handed dominant is considered probability of success. We could do it the other way, and things will come out the same, but we're going to do it this way. So, sample size 59, probability of success again is 0.11. And we are going to run binomial distribution. We're going to do it on stat test. So we'll analyze probability distribution, binomial distribution. Fixed number of trials 59, probability of success is 0.11. Hit evaluate. Okay. So we get a whole lot of numbers here as we go down. Notice our mean is 6.49. That's what we had as expected. Gives us a standard deviation, gives us our variance. Then it gives us a lot of these different probabilities. So again, number of right-handed students percentage was 0.89 and non-right was 0.11. This was 52.51. This was 6.49. I got these from what we did earlier. So I'm just kind of going from what we had up here. 52.51, 6.49, and 89, 11%. Okay. So we want to find the probability of exactly our expected number of non-right-handed students. Okay, so our expected number was 6.49. So we're going to look at 6 here and 7. So we're looking at probability somewhere in between. So I'm going to round it to 0.16. 0.16. Basically a 16% probability that we get exactly 6 or 7 students that are non-right-handed. And the probability of less than our expected number, well, let's make this really a bit simpler. Let's round it up to 7. So our expected number will round up to 7. So about 0.5, well, I'll still round that 2 digits. So 7 will be for x or fewer, 0.68, 0.68, and then more is 0.48. So we're rounding these. So I rounded this up to expected number of 7. The reason I rounded it up is, I don't know, I just did. Because you can't have a 0.49. I didn't really want to round it down. Alright, so the mean of our binomial distribution again is 6.49. Calculate the standard deviation. That would be 2.4. Based on range rule of thumb, what is the minimum? Well, that's going to be 6.49 minus 2 times 2.4. So 6.49 minus 2 times 2.4. That's 1.69. The high value would be adding 2 times 2.4, which is 4.8. So 1.69 to 11.29. So how many right-hander students did we have in our sample, or non-right-hand students did we have in our sample? Well, we ended up with 5 lefts and 1 both, so we ended up with 6. Okay, which, is well within our range. It's right there with what we expected. So yes, our number does fall within our range of usual values. Right, so we are not surprised that to have 6 non-right-handed students in our sample. And so based on the theoretical probability of our non-right-hander students, we cannot dispute the percentages. If we had something higher, maybe if we had 20 left-hander students, then maybe we can say, okay, well that didn't really follow the right, the right thought with that. Alright, so the next thing is going to be bear versus a swarm of bees. Same idea with this. Percentage though, we'll kind of come up with a theoretical percentage. So we're going to do 0.5 for both. We still have 59 students in our sample size. So our expected number is going to be, the 29.5, which is 59 times 0.5, right? Make sure I do my math right. Yeah, 29.5. And that's going to be for both. Okay, because it's all equal here. Okay. Again, do we meet all 4 of the requirements? Well, n equals 59. Each student is independent. It's either going to be a bear or a bee. And the idea is we're going to assume our probability of success is 0.5, and that's kind of what we're testing here. So it does meet the probability of the requirements for binomial distribution. Alright, so same idea. The only thing we're going to do is change the p-value with this really. So 59, so sample size, p-value is 0.5. So we come here, analyze probability distribution, binomial, 59.5, and we get mean 29.5, standard deviation 3.84, and then all these based on the 59. So we come down to expected value, we're about 10% here for 29 or for 30. Alright, so for probability of exactly our expected number, we're going to assume now, and I'll go with our expected number being 30. For each of these. It's close, I'm rounding up. Right, so for the bear, 30.10, and for the attacker bees, you're looking at pretty much the same 0.10 because it's going to be the same numbers here. Probability of less than our expected number, you're looking at 0.606 or 0.60, 0.6, and that's going to be the same because you're basing on the same average. And then the probability of more than expected number is 0.5. Right. Right, so mean 29.5, standard deviation 3.84. Based on this, we are looking at, let me get my calculator out, 29.5 plus 2 times 3.84. Oops. Oh, okay. I didn't mean to put the parenthesis. And 29.5 minus 2 times 3.84. So 21.82 is a low value. 37.18 is a high value. And in our sample data, which we hadn't taken yet from here, I know it was like the last one. There we go. Column 2. And then we can sort it by column 2. So bear all the way down to 34, and then bees all the way to the end. All right, so 34 bears B's is 35 and down. What was our success that we were looking at? Being mauled by a bear. So we had excess. People would rather be mauled by a bear of 34. And this is not unexpected, given that it falls in our usual range between 21.82 and 37.18. Alright, it's a little bit towards the high end. Right, so we cannot really change, we can still assume that the percentage is a 50-50 split between choosing the being mauled by a bear or attacked by a swarm of bees. Alright, so again, 34 is what we had here. Oh, I meant to put that in there. That, yes, it falls in the range. Alright, so one thing we also can do is we come back to this. Let's go back to the binomial distribution. Put in the 0.5 again. Put in the 59. We can look at 34. So I'm going to put in 34 for x. Okay, I didn't do this with the last one because, we get right there around our expected. But we can see to actually get this amount, expected amount, is a 5% chance. But it's, a 90% chance of getting 34 fewer and 50% chance of getting 34 greater. But 5% chance isn't, that, strange. It's a little on the high end, but not by much. Alright, I think that's the end of this. Yes, that's the end of this. Alright, so that is the end of this particular project walkthrough. Now, again, your numbers may not match. So, I just want to clarify this before we end this. Solutions may not match current data. And again, that's because we are each semester adding more data to each one of these. And so it may not match up. Just want to address that. Okay, so I will see you in the next video.